начинать. Let me recall you what we did last time to description of the probability measure on the infinitely dimensional Banach space. So we have Banach space, which is real and separate, with the norm which you denote as usual in such a way. We have a set B star, a set of continuous linear functionals on the space B, norm here is the norm in the conjugated space. We know that due to separability of the that all functions from there are measured, and due to this fact, it is expected that if we have such a mappings F1, Fn, which maps B into Rn, F are the elements of the B star, and have the measure mu F, Fn, which is defined like image of the initial measure under this mapping. Of all such measures will be sufficient to determine uniquely initial probability measure mu, and it is true. But what we invented last time, we invented that first of all, the set of such measures must be consistent. So the family of such measures, so-called finite dimensional distributions, cannot be arbitrary. The relationship between different mu, F1, Fn, which corresponds to different sets of linear functionals, are more or less the same, evident exactly as for finite dimensional distributions of random processes, as we know from the theory of random processes. But what occurs is that even if we have consistent family of a finite dimensional distribution, it does not mean that you have a probability measure on the space B. Actually, the problem is more or less the same as we face in the discussion of continuity of trajectories of the random process. Maybe you remember that if we know finite dimensional distribution of the process, then it can happen that process cannot have even continuous trajectories, continuous modification. We have to add something in order to embed our process into the space of continuous functions. More or less the same happens here. So today we will discuss what we have to add to the family of finite dimensional distribution in order to have the probability measure on the initial space B for which this formula holds. So let us begin with the well-known remark, which sometimes is called Ulam theorem, about the concentration of the any probability distribution on Banach space on the compacts. So I will consider the general formulation. It is not necessary now to have linear structure on the space. So we will discuss the space, which is just a metric and complete and setup. So let me formulate first of all the statement. Then we will discuss the proof and discuss corollaries. So I will suppose that X rho is a complete separable metric space. I just recall complete means that we have the limit for any Cauchy sequence in this space. Separable means that we have a countable set which is dense in this set, in this space. And I will consider mu, which is a probability measure on the Borel sigma field. Borel sigma field. Then for all epsilon which is positive, there exists compact set K epsilon such that mu of K epsilon is greater than 1 minus epsilon. This is theorem, and as I said, sometimes it is called Ulam theorem. So we have such statement. For any epsilon which is positive, we can find such compact that our measure mu is concentrated on this compact up to the small part which is smaller than epsilon. It is interesting thing. Because, as we will see further, compacts in infinitely dimensional Banach spaces have a very special structure, and we can say that they are very slim sets. But before to discuss compacts in Banach space, let me recall you the notion of compact and arbitrary metric space. Then we discuss criterion of compactness, and then we will prove this theorem. So let me recall you what is compact now. we will say that K is compact subset of X if for any open covering. K is alpha J alpha, where J alpha is open for all alpha. There exists finite subcovering. I will not write because of small words, but I will write the formula that it is covered by finite subcovering J alpha I. This is a general definition which can be applied not only for the metric space but also for topological spaces, so on. In case of separate metric space, one can substitute this definition as follows. K is compact, so in our case of metric space, K is compact if and only if any sequence of elements of K contains subsequence which is convergent to the element of K. So it is useful reformulation for metric spaces that K is compact if any sequence I will say it in such a way, but it can have repeating members. Contains subsequence X and K such that X and K tends to X star, which also belong to K when K tends to K. So in our case of separate metric space, these are equivalent definitions.
This is for all metric spaces or only for separable?
I said for separate metric space.
Oh, okay.
So this is the equivalent formulation in our case, and we will use it sometime. And what is much more important for us that we have a Hausdorff criterion for set K to be compact. Namely, again, we have a metric space X which is complete. Then we have Hausdorff formulation, Hausdorff criterion. This is theorem that K is compact if and only if for every epsilon which is rated as a zero, there exists a finite number of elements of N the number and elements, of course, can depend from itself, which belong to K, such that K is union of K belongs to union of the open balls with the center on this in these elements. X, and radius. Sometimes this set centers of the ball x1, xn is called epsilon net for the set K. It is not hard to prove this theorem, and it is known from the regular courses on mathematical analysis. What is interesting for us, and it can be a small but useful exercise, that it is not necessary to require that these elements belong to K. So if one can find epsilon net, which consists of elements of all space X, it is enough to say that K is compact. Excuse me, for K, and K is closed. K is closed. Of course, we need this one. And K is closed. Okay. And so we have closed set, but in order to check that it is compact, we have to check that for every epsilon it has finite epsilon net. This works only in the complete metric space. If space is not complete, it is not true. And as I said, it is useful to solve exercise that it is enough to find epsilon net, which consists of element not K, but from all space X. We will use this theorem, this criterion, when we'll prove Ulam theorem. Now let's prove it, and then we will discuss examples of compacts and examples of the distributions on Banach space in order to understand what does it mean, this Ulam theorem, for our investigation. Okay. So let us prove our theorem. Recall condition: X rho is complete separate, and mu is a distribution, is a probability measure on the Borel symmetry. Now let us proceed as follows. I will try to construct the set for fixed epsilon, set K epsilon, compact set K epsilon. So I will suppose that epsilon, which is positive, is given. Then what can we do? Let us try to use separability let us try to use separability of x. Since x is separate, then x can be represented as a, excuse me, maybe, then for any n which is greater than 1, x can be represented as follows. X is the union of the counter set of open balls x and k. I use double numeration in order to emphasize that centers of the ball both depend on the number n, which is here, and radius 1 or yeah. So this is due to separability of the space X. Now I will use the fact that mu is a finite measure, it is a probability measure. So for any fixed n, I can find the finite number of this ball, which have a sufficiently large measure. Let me proceed as follows. Due to the measure mu is probability measure, then mu 1, which is equal to mu of x, is a limit under n capital tends to infinity, mu of the finite union of this balls k equal 1 to n capital d x and k 1 over. Yeah. So let us take such n. It's necessary to write something. I will take such n which depends on the n small in a way that mu of this union k equal 1 to n capital N small d x n k 1 over n is greater than 1 minus epsilon 2 n plus 1. Yeah. Or even maybe plus 1. So this is due to the continuity of the finite measure from below. Yeah? Now let us construct our set K as follows. K equal to now let's take some operation of the set. This is intersection 1 and equal 1 to infinity of this unions. Here is k equal 1 to n capital with small n index b of x and k 1 over n. And then I will take it. Okay. Okay. Then first of all, let us check that this set is compact. It is not hard to. Excuse me?
I'm sorry, the balls are open or closed?
here walls are open. But
Uh-huh.
now I take a closure. Yeah?
Mhm. Ah, okay. Yes, I didn't notice. Sorry.
Mhm. Again, K is constructed as follows. We take intersection of these finite unions and then take a closure. This is a symbol of closure. I use this. This is not a complement. Yeah, this is symbol of closure in the initial space. Then let us check that K is compact. Let us recall that our space is complete metric space, and for any n which is greater than 0, these centers x and 1, x and capital N is at least 2 or n net for K. Yes, because K belongs to the closure to the closure of this union. So because of finite, it belongs to the union of closed walls, and I just take 2 over n, not 1 over n, just to be sure. So we have the finite epsilon net for K. By the way, here I already use those. I already use those set those exercise that epsilon centers of the epsilon net can be not in the space in the set K itself. It is enough to find finite epsilon net from the element of the space. This is our case. So we have finite epsilon net, and of course K is closed by definition. Due to this to relation, subset of X. Now let's estimate the measure mu of K. I will erase this one. I will erase this one, and now let me mu of K is greater or equal than mu of this intersection B X and K 1 over n. And now, in order to estimate this one, I will estimate the measure of X of of the difference X minus this mu of X minus this intersection. is the mu of the union of the difference is equal mu of the union n equal 1 to 50 x minus this finite union k equal 1 b x and k 1 over n, and is less than or equals in the sum from n equal 1 to infinity. Here is mu of x minus x minus union from k equal 1 to n and b x and k 1 over n, and it is less than, because of our choice of this n capital index n, I will write here, it is less than sum from k from n small equal 1 to infinity epsilon over 2 n, which is equal to epsilon. That's all. So we already check that our measure is concentrated on the set k up to the small epsilon. Now let us try to understand what we get. In order to do this, we have to look on two things. First one is the exempts and properties of the compounds in Banach spaces. Second one is the exempts and properties of measures, probability measures in Banach spaces. And then we can understand what does it mean that measure is almost concentrated on the complex. First of all, before we go into the content exempts, let me recall you interesting property. Maybe you remember a lemma about almost orthogonal vector. So if we have some subspace L, which is closed, this is closed linear subspace of B such that L is not equal to B, then there exists X which belongs to B such that then for all epsilon greater than 0, there exists X which belongs to B such that norm of X equal to 1 and distance d of xl is greater or equal than 1 minus and we call this element by almost orthogonal vector to subspace L. This is very useful lemma because of we have no angles in arbitrary Banach space, but we can use this lemma as follows. You remember maybe the Gilbert picture. If we have Gilbert space, then of course one can find just a vector which has unit norm, and such that it is orthogonal to this subspace L, which is proper subspace, which is not equal to all space. But if we have no angles, what happens? We still can find the element which has the length equal to 1, such that the distance. I don't know what is this angle. I don't know even about the uniqueness of realization of this distance. It can happen that it can be realized on a number of vectors, not on the one vector. It is interesting. Yeah. So, but this distance is greater or equal than 1 minus epsilon. So it is almost orthogonal. Okay. Due to this lemma, we can proceed as follows. We can say that ball in the infinite dimensional Banach space is not compact. Yes, we already mentioned this already. That if I have, for example, union ball, it does not matter close or not, in our Banach space B, then B 0, 1 and dimension B is empty, then B01 is not compact. So our space is not compact, but is not locally compact. But what is much more interesting, that even if we have some set A, excuse me, maybe I will write now already compact. Suppose that K is compact in B. Then under this condition, K has not interior points. So inside of K there are no any balls. Yeah, it is slim. It is like something which we face on the surface of the sea when sea is not quiet. Yeah. So K has not interior forms, and we understand that our probability measure must be almost concentrated on this bad set. It does not contain any balls. Yeah. Now, in order to understand the possible structure of the compacts, let us consider examples of compacts in different Banach spaces. Of course, it is good to start from the Hilbert space because it has a more rich geometric structure. Maybe not more rich, but more common for us geometric structure. More or less, we can say that a Hilbert space inherits some properties of the Euclid spaces. Now, let's start from the examples of compacts. First one, consider H Hilbert space, and because we are considering separable spaces, and we know that separable Hilbert space can be described via coordinate approach if we fix some basis. So I will discuss not general H, but L too small. How we make the isomorphism now? We just take orthonormal basis n is orthonormal. And if we consider element x from H, it is uniquely represented as the sum from n equal 1 to xn en, where the sequence of n xn belongs to L2 small. And this is one-to-one correspondence. Moreover, it keeps the norm, so this is isometry between our arbitrary central Hilbert space and L2 small. For consideration of the compacts, it is enough for at least for the first one. Let us consider now compacts in L2 small. First of all, I want to propose you general criterion when the set K will be compact in L2 small. So I will consider always closed set. Yeah? So closed set. Okay. Is a compact if and only if such relation holds supremum over K, sum from n equal to n capital to infinity, xn square tends to 0 when n capital tends to this one. So we have such condition that the series which defines the norm for the element of K must converge uniformly. Because we remember that for any element of L2 small, the series from n equal 1 to infinity of its coordinates, of squares of its coordinates converges. But it occurs that criterion of compactness is the uniform convergence of such series. And it is not hard to prove this criterion. Let's do. So let us proceed with the fact that this condition is necessary. Suppose that K is compact. K is compact. In order to check that this condition holds, I have for any epsilon find such number n that this supremum is less than epsilon. I will do it as follows. If K is compact, then then it has epsilon net. Then, due to Hausdorff criterion, there exists there exists epsilon naught. Then it means that there exists such x1, xm, that k is belongs to the union of the open balls B, X, G. Now let's see. Let's see the series for coordinates for norm of these fixed centers.
We take the centers from the K, yeah? Not any epsilon n.
No, it is, as I said, in a lot of applications, it is not necessary to have it in the key. It is just arbitrary.
Okay.
We do need centers inside of the K. When we discussed the continuity properties related to Kolmogorov entropy, because we have not only number of covering balls, but number of the so-called packing number. Try to find inside of the K maximal set such that pairwise distances are greater than epsilon. And there are relations between this packing number and covering numbers. But now it is not necessary to check that these elements are from K. They are arbitrary, but for us now it is more important that we have finite number of such balls. Then let us consider series. I already put here maximum from G equal 1 to M. Here we have sum from N equal N capital to infinity. Here is X J N square. I put here two indices in order to emphasize that this is the nth coordinate of the element xj. And we know that due to the finite number of the series, they are converging uniformly. This tends to 0 when n tends to infinity. Due to this fact, one can find such there exists such n. Here, for example, z. Okay, let me denote this by r and capital. That r and 0 is less than some epsilon. Okay, now let us consider arbitrary element x now from the set K, from this set. Consider arbitrary element x which belongs to K. Then what happens? If I consider the sum from n equal n0 to infinity of x and square. How I can estimate? I know that this x belongs to some wall b x j. For example, okay, bxj. So what I can do, I can just say that this is less or equal than less or equal than 2 multiplied by sum from n 0 to infinity. Here is xn minus x and jn square plus the sum from n equal 0 to infinity x jn square. I know that this is because of this relation is less or equal than 2 epsilon square, yes? And this is less or equal than epsilon by the choice of answer plus epsilon. Yeah. Of course, here is not epsilon finally, but it is understandable that this is enough. Yeah. If somebody wants, he or she can do this makeup by itself. So we understand that our series for norm are convergent uniformly with respect to k. This is the one way, and another way, sufficient condition, also is not very hard to check. And sufficient condition is the following. Sufficiency can be checked as follows. What we need, because k is already closed, k is closed by our assumption, then it is enough to find epsilon net. We take epsilon positive, fix it, and try to find epsilon net. Okay. Again, let us recall that now we have the following. There exists some n0 such that this remaining term, maybe it's better to say sup over k, here is sum from n small to n equal n0 to n2. Here is x n square is less than, okay, let's try to be very careful here. Okay, one can find such n0. Yes, such n0. Then what we do need. Also, we know that this sup over k, this is a sequence, so I just take the first. This is less than and equal to 1 to infinity. This is the first number of our sequence. Let's denote it by some L. Then now let us consider the trace of K in the finite dimensional space. Consider the first coordinates of K are from 1 to n0. So, if I consider such vectors, let us denote it by K and 0, this is what? This is such sequence x1, x and 0, 0, 0, 0, 0. So this is a projection of K in the first coordinates when x belongs to K. It is bounded, it is closed set, so it is compact. It's compact in R and 0. Due to this, one can check. Due to this, one can find epsilon net point, epsilon 2 over 2 net point. So, now y1, ym is epsilon over 2 net. Net for this K and then now let's organize infinite sequence from this. So I will take yj with theta equal to here is yj1, yj j2, and so on, yj and 0, and then 0, 0, 0, 0, 0. So now, now I have such infinite sequence, and then it is not easy to not hard to check that these vectors like m organize which organize epsilon 2 plus epsilon 2 net is epsilon net is epsilon net for K. So we understand that K satisfies Hausdorff criterion, and this is end of our K's compact. In this simple statement, we have a partial case of very powerful but not strictly formulated criterion of compactness in any Banach space. We will check this in the next lecture. That if we have some condition which defines the norm in Banach space, for example, a function must be continuous, or some series must converge, and so on, then compact set is exactly the set where this condition holds uniformly. You remember a scalar cell. The continuity must be uniform with respect to the element of the set. This way, this example. Here we have the norm, the series from the coordinates square must converge. Compact, it must converge uniformly. And next lecture we will see another example. This is a powerful tool how to understand which set must be compact in arbitrary Banach space. But before we will go Banach space next lecture, we will consider concrete compacts which are very useful for us in the Hilbert space. But we will do this next lecture. For today, that's all. Thank you for your attention. Maybe somebody have questions.
No questions. Thank you very much.
Thank you for your attention again. And